Nice to meet you. I'm Khadr Choktai and you're watching my YouTube channel School of Advanced Chemistry. Today I'm going to discuss IR spectroscopy, a technique that is used to locate the functional group of organic molecules, especially or different other covalent molecule. This is the basic part of your A-level chemistry syllabus. Let's jump into it. IR spectroscopy is basically used, this technique is basically used to diagnose the functional group of organic molecules and other diagnostic of simple covalent molecule. Let's see what is this technique. First of all, what are the IR radiations? IR mean infrared radiations. Infrared radiations are the part of electromagnetic family or the electromagnetic spectrum. Electromagnetic spectrum is having different sort of radiation, and IR radiation, infrared radiation, is the part of that electromagnetic spectrum in which there are gamma rays, there are X-rays, ultraviolet, visible rays, microwave rays, and radio rays or radio frequency rays. Infrared radiations are the part of this electromagnetic spectrum, and they started from, their frequencies start from 10 raised to power 12 to almost 10 raised to power 14 and so on. These are quite important radiation as far as our daily life is concerned. We use different sort of remote controls, and those are also facilitated by these radiation. I mean, with the help of these IR radiations, we can control different devices, and these are invisible radiation. These cannot seen by the human eye. The next one is when IR radiations are allowed to react with chemical bond. I mean, this is the spectroscopy. Spectroscopy mean a technique in which radiations are supposed to interact with a chemical bond. When electromagnetic radiations are supposed to interact with the chemical bonds, or when they are going to hit with a chemical bond, and they change the modes of vibration. Every molecule, inside the molecule, different bonds are vibrating around its central atom, and there are different sort of vibrations, different modes of vibration: wagging, stretching, bending, scissoring, and so on. We are not concerned with the mode of vibration in this syllabus as far as Cambridge AS chemistry syllabus is concerned. So what are the basic function? What they do when they are allowed to react with the chemical bonds? They hit with the chemical bond basically, and they change the amplitude of modes of vibration or the nature of the vibration. So after absorption of IR radiation, there is the different behavior of these chemical bonds. However, they are not going to break them out. There is no change in the chemistry of molecule. There is no change in the formula of the molecule, but there is change in the vibrational movement of the molecule. Let's see over here. Basically, what is the basic procedure? A beam of IR radiation is passed through the sample of organic or covalent compound. A beam of full spectrum, of IR radiation, you can say a convoy of IR radiations are allowed to pass through that sample, through the sample of an organic compound that is having that OH bond, C double bond, O bond. Organic compounds having the different sort of functional group. There may be the presence of C double bond O group, like in imide, like in esters, like acids, like ketones, like aldehyde, and so on. There may be the presence of OH bond, like in acid, like in alcohol. There may be the presence of C single bond O, like in ester, like in acids. There may be the presence of C single bond N in amines. There may be the presence of C triple bond N, that is the part of nitrile. So basically, these radiations, when enter into the solution of organic compound, these are absorbed by the polar bonds. These are absorbed by the polar bond of that molecule. Polar bond, basic, highly polar bond of the organic molecule. After absorption, these radiations increase, as I told you, the vibrational energy of the bond. As they are different type of vibration, stretching, bending, wagging, each bond may absorb one or more than one wave number or more than one wavelength radiation or more than one frequency radiation, and it may show different sort of signals, different sort of peaks, you can say. I mean, a single bond, a single group, a single bond may absorb the different wavelength according to its nature of vibration and so on. We are not concerned with the explanation regarding the modes of vibration, why they are going to absorb different radiation, what is the reason behind it. We are basically concerned with the IR radiation to find out the functional group of organic compound. So the next one is similar bond in the different environment absorb different radiation. For example, OH group is present that may be the part of an alcohol, as I told you earlier. OH group may be the part of carboxylic acid. So OH group, it may be the part of alcohol. OH group may be the part of carboxylic acid. So under these different circumstances, under these different environment, these OH group will absorb IR radiations of different frequency or different wavelength. So in this way, the nature of wavelength of or the nature of wave number of the radiation that is being absorbed at that time by a specific bond is the characteristic property of that bond. I mean, OH group of the carboxylic acid will absorb different wavelength radiation, different wave number IR radiation, and OH group of the alcohol will absorb different wave number radiation from the IR spectrum. Radiations that emerges, after the absorption of the radiation, those are unabsorbed. They are said to be the transmitted radiation. Radiations, those are unabsorbed, some were absorbed, those are yet unabsorbed, they transmitted towards, outside the sample, and that is basically noted by that machine, by that instrument. And as I told you, we are going to mark wave numbers, or we are going to measure the different wave number radiations. Radiations with respect to their wave numbers, how many different type of wave number have been absorbed, and the rest of will be transmitted. So let's see over here, this is said to be an IR spectrum. Now let's see what is IR spectrum. IR spectrum is basically a graph that is having x-axis, y-axis, and between these two axes, there are different signals or there are different peaks. The portion of IR radiation that was not absorbed, that is said to be transmitted radiations. And we are going to check them into percentage transmittance. On x-axis, we are taking the wave number in per centimeter. We are taking wave number in per centimeter. Basically, we are going to meet these two factors, percentage transmittance versus wave number, and we are going to have this sort of curve or curves, you can say, and these are called peaks or signal. Area under the peak, that is highlighted by the yellow color, this area is indicating the transmittance of these radiation. The radiations from IR spectrum, those haven't absorbed, they are shown by this yellow area. I highlighted this area for the sake of difference between the absorbed radiation and to differentiate, between the absorbed and unabsorbed radiation. This yellow area is basically indicating unabsorbed radiation. This is unabsorbed. Unabsorbed is also said to be transmitted radiation. So these radiation, or the portion of the radiation, or these numbers were almost, it was not absorbed by that sample. Now, what are the absorbed radiation? I highlighted that area with a red mark, basically. These radiations are said to be, or this area is said to be the absorbed. Percentage of the different wave number that have been absorbed by that sample is shown over here. This is absorbed peak, absorbed. All this red highlighted area is showing the absorbance. So we are going to read it out there is reading the spectrum inversely, you can say, or we are going to read them out towards x-axis. So this is one peak, this is the second peak, third peak, fourth, fifth. Major peaks are over here. Those are lying in this spectrum, or these are said to be the basic absorbance. So here is the absorbance, 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 absorbance. These are also minute absorbance, you can say, but these are called major absorbance. So these red portion lines, red portion wells, you can say, these are indicating the absorbed radiation by that IR spectrum. In this case, basically, we are going to check the wave number of each absorbance. This is the peak that is showing this absorbance. That is absorbing almost 3000 wave number IR radiation. This peak is absorbing almost 1750 per centimeter wave number. Same is the case, this peak is absorbing almost 1200 wave number radiation, and so on. So basically, the spectrum is read out from its x-axis, and they are basically the characteristics peaks, characteristic absorbance. From these number, we can diagnose the different polar bonds present in that molecule, and after joining that polar bond, we can construct an overall functional group of the molecule. This region is said to be fingerprint region. The region that is from 1000 to 1500, basically this x-axis is moving from right to left. And this region that is starting, that is moving till 1500, it is said to be the fingerprint region. And basically, as far as the Cambridge chemistry syllabus is concerned, you are not going to deal with this region. Most of the functional group that will be asked in your syllabus, that will be from the other portion. Beyond the 1500, you are concerned with the spectrum, and you will diagnose OH bond, C double bond, and so on. So major functional group that is present, that those are present in your syllabus, that will be from the region away from or beyond from the 1500 centimeter wave numbers. The next one is data booklet or data table. In data table, there are basically different columns. Column number 1, this is showing the bond, nature of bond. It is showing the functional group containing the bonds. And this one is showing the range of absorption. And the last one column is for strong and weak signals. Sometimes there is the indication of very broad peak or sharp peak. So according to this table, we are having 4 different relationships for one polar bond, for one molecule, you can say. In case of alcohol, esters and ethers, C single bond O may show absorbance at 1040 to 300 wave number, and its signal will be strong. The next one, C double bond O will show in this region absorbance, the peak, you can say. Same is the case, C double bond O, it may be from amide, from aldehyde, from acid, from ester, and so on. So they will show different sort of absorbance with respect to different wave number per centimeter. However, this S stand for strong and W stand for weak. W stand for weak. Generally, I'm going to show you what is the strong and what are the basically the weak peaks in my next few slides. Now come towards the application. This technique helps to identify the functional group in organic compound basically. Some functional group can be located or can be derived, can be assessed by the combination of different bonds, different type of bonds. For example, in case of ester, there is the presence of C double bond O and C single bond O. Only these 2 polar bonds are present in an ester linkage or in a simple ester, you can say. But if the compound is having C double bond O peak, if the compound is having C single bond O peak, and that is also having OH bond peak, it means that it's not an ester, it's a carboxylic acid. So by the combination of different polar bonds, by the, watching the different peaks at different wave number, we can assess, we can guess, we can construct an overall functional group of the organic compound. Similarly, IR radiations, IR spectrum, infrared spectrum, air pollution like CO2, CO can be detected in a sample by IR spectrum or IR technique. So this technique is also quite helpful to diagnose some inorganic covalent molecule like CO2, like CO, carbon monoxide, that is also having the polar bond. So carbon monoxide, C double bond, triple bond O, and CO2, these are the two pollutant gases. So these can also be diagnosed, these can also be checked with the help of this technique that is said to be IR spectroscopy. The next one is the application, and I'm going to show you what is the difference between the sharp and the broad peak, and what is the difference between strong and weak signals, or what is the strong and what is a weak term that is used for the signal. Basically, I'm going to divide this whole spectrum into two portions. I'm cutting this signal imaginary from 50% of this whole picture, of this whole graph. The lines, those are crossing towards x-axis from this 50% line, from this half spectrum. These are said to be the strong peaks. These are said to be the strong signal. If the peak that is touching at the middle line, that is at 50% almost, these are said to be medium peaks or medium signals. Peaks, signal is one and the same thing. And if the peaks, those are very much above in this spectrum, they are said to be the weak peaks or weak signal. So strong signal will be more towards in depth towards x-axis, and the weak signal will be at higher level. The next one thing is sharp versus broad. As it was weak versus strong, similarly there is a sharp versus broad. This peak, just have a look on this peak, that is having more wider upper portion than its bottom portion, its lower portion. So this peak is said to be broad peak. Come toward this one. This is a needle-like peak, a pencil-like peak, and this is said to be the sharp signal or sharp peak. So this shape of peak is said to be sharp shape, and this shape of peak is said to be the broad peak, or sometimes we call it very broad peak. Again, it's a sharp peak, it's a broad peak, it's a sharp peak. So sharp versus broad. Either the peak will be sharp or broad, or the peak will be strong, weak, or medium peak. So this is the weak signal, this is the medium signal, and this is the strong signal, strong peak. It is absorbing maximum radiation. I mean, it's moving or touching, or that it's is very much closest to the x-axis. Next one, let's talk about the different example. This is a spectrum of ethanol, aldehyde basically. And once again, I'm going to cut this spectrum into two portions, roughly into two portions. So the basic strong signal is lying at 1700. At 1700 wave number, it means that from checking the data booklet, we can say that this compound is having basic major polar bond is C double bond O. There is no any other basic polar famous group. So that's mean either it may be an aldehyde or it may be a ketone. Either it may be an aldehyde or it may be a ketone. So this is the typical aldehyde, you can say, generally speaking. It's a spectrum of an aldehyde that is having only one strong peak, sharp peak, that is lying at 1700. As I told you, we are concerned with a spectrum that is beyond the 1500 wave number spectrum. Just have a look on the next example, that is an alcohol, ethanol basically. And you should remember the shape of this molecule, this OH group basically. This is the shape of OH group. This is a broad peak, and it is almost touching, almost, not exactly, it is almost touching the x-axis, and its number is almost, you can say, 3300 wave number. This is a broad peak. This present in lower portion of the spectrum. I mean, it is very much close to the x-axis, and its upper portion is quite wider, and it's a broad peak. It is said to be the broad peak, and it is a typical peak for the OH group that is present in an alcohol. Now, let's see if the OH group is present with C double bond O. With C double bond O, I mean in ethanoic acid. Again, here is this one OH peak. This is also for the OH peak. And this is the very broad peak. I mean, its upper portion is much wide as compared to its bottom. So it is said to be very broad peak, and it is not very much closer to the x-axis. It is, I mean, almost, you can say, 75% absorbance, almost you can say. And this is in front of, or its absorbance is located almost 3000 wave number. So OH from the carboxylic acid will be lying in front of 3000 wave number. It will be very broad peak. It will be at, I mean, away from the x-axis, you can say. And once again, you will have to notice it, and you will have to memorize the shape of this peak. It's a distinct peak for especially all type of carboxylic acid. Moreover, as you know, there is another peak, strong peak present at 1700, C double bond O, and here is the peak of CO. But usually we are not going to concern with the CO. However, from using the data booklet, we can find the answer of different other signals or peaks. Those are present in this fingerprint region. Mostly they are asking the peaks, those are present beyond the fingerprint level. I mean, those are having more wave number than that of 1500. Now, for the sake of comparison, I'm showing you the two spectrum. Both are having OH group. One is alcohol ethanol, and other one is carboxylic acid. Just have a look. So once again, this is the OH peak touching almost the x-axis, and this portion should be in your mind. This picture must be visualized whenever you are going to solve the past paper questions. And similarly, this OH peak is very broad peak, and it is lying at 3000 wave number. It is lying at 3300 wave number, and this peak is very broad peak. This is simple broad peak, and so on. So there is the clear differentiation between the spectrum of carboxylic acid and the spectrum of alcohol. Moreover, in case of carboxylic acid, there will be another peak, that is C double bond O peak. In case of simple alcohol, there will be no any major peak, I mean no any strong signal will be there in front of 1700 wave number. CO peak will be present in acid, and there is no peak at 1700, strong signal in 1700 in alcohol or ethanol, I mean. The next one is the application, general application of the whole radiations as far as the atmospheric pollution is concerned. I mean, atmospheric pollution and IR spectroscopy are also having the good relationship. IR spectroscopy is very much useful to diagnose greenhouse gases. Atmospheric pollutants can be diagnosed with the help of IR spectroscopy, and IR radiations can be used to diagnose the greenhouse gases in the atmosphere. IR radiation absorbed, these radiations are absorbed by the basically, as I told you, carbon monoxide, carbon dioxide, water, methane, and so on. I mean, methane is a greenhouse gas, carbon dioxide is a greenhouse gas, water is also a greenhouse vapors or gas, you can say. So basically, these radiations are absorbed by these sort of pollutant gases, and these are not absorbed. These are not absorbed by oxygen. These are not absorbed by nitrogen. So there is a clear-cut indication of pollutant gases if they are present in air in coordination with oxygen and nitrogen. So we can diagnose the presence of water, we can diagnose the presence of carbon dioxide and presence of methane gas as well. Why oxygen and nitrogen cannot be detected by IR radiation or IR spectroscopy? Because they are non-polar gases. These are having no polarity. Oxygen and nitrogen are non-polar gases, so they cannot be located, they cannot be checked with the help of IR radiation. Once again, IR radiation is quite helpful to diagnose the pollutant gases in the atmosphere. That's all about the core of this lecture. Now I'm going to solve past paper questions. Question number 1. H and I are the isomers with molecular formula C2H4O2. The IR spectrum or IR spectra of the isomers H and I are shown over here. In this picture, you can see that there are the two major peaks. One is lying over here at 1700 wave number, and this is the very remarkable peak. A famous peak that is showing the OH group that is almost lying at 3000 wave number, and this is the OH group of carboxylic acid. So this C2H4O2 is a carboxylic acid, as it is having OH group over here, a very broad peak, and it's lying at 3000 wave number almost. And here is the presence of C double bond O peak at 1700. However, if I'm going to check in the fingerprint region, here there is the presence of C single bond O P. So this H is basically a carboxylic acid, and it is CH3 C double bond OH. It's an ethanoic acid. So by seeing this OH group, a prominent peak, by seeing this one C double bond O peak, by seeing noting this C single bond O peak, we can conclude that this is an ethanoic acid. Its isomer is over here, that is said to be or named as I. In this peak, once again, in this spectrum, once again, I'm going to divide into two parts, this whole page, this whole spectrum. And now this time we are having basically two peaks. One is in fingerprint region, and this one is beyond the fingerprint region, 1500. It is showing the presence of C double bond O. You can check it from the data booklet. It is present at 1700 wave number, and it is lying for C single bond O peak. So there is no OH peak. There is no such very broad peak, So this is an ester. Basically, an ester is the functional group isomer of carboxylic acid. An ester can be a functional group isomer of carboxylic acid. So it is 2 carbon ester. Its formula will be like that: HC double bond O, and here is CH3 OCH3. I'm going to write it again. CO and CH3 over here. So this is methyl methanoate I. I is basically methyl methanoate. Next one. The IR spectrum was obtained from the compound J. Again, roughly speaking, I'm going to divide it into, roughly dividing into 2 portions. One is the peak over here, other one is over here. These are 2 basic major peaks, you can say. Which statement about the J is correct? Basically, this peak is about, as I told you, C double bond O at 1700, And this sharp peak, this one, if you see the data booklet, it may be of CH peak, CH group peak, you can say. But the basic question is, he is saying CO and C triple bond N peaks. I mean, this question is related to the peaks C double bond O and C triple bond N peak. Let me jump once again towards the data table. Let's see over here. In case of C triple bond N, if the C triple bond N is present, then a weak signal should be there, and signal must be at 2200 to 2250. I mean, if the nitrile CN group is present, we have find one group, that is C double bond O, that was present almost at in the range of 1700. Now the second one, as he is asking in the question, if the C triple bond N is over here, then it must be lying at 220/2250, and this is the weak signal or weak peak. So there is no any sort of peak in this region in 2250. So there is the presence of only one group C double bond O. Only C double bond O is present, but no C triple bond N is present. C is the correct option. The next one. This spectrum compound X has infrared spectrum, and the spectrum is showing different peaks. As you can see, what could be the identity of compound X? Once again, divide this spectrum into roughly 2 into 2 portions, and these peaks are said to be the main peaks or the important peaks. You can see that it's a very broad peak, so it is having OH group that belongs to the member that is having the C double bond O in its proximity, that is the member of carboxylic acid. This very much typical peak for C double bond O, and it may be for CO. So it means that C double bond O is present, CO is present, and OH bond is present over here. So this is a carboxylic acid. Only one option is having acid, that is A, ethanoic acid. That's all about today. That's all about this basic, major, comprehensive lecture of IR spectroscopy for A-level Cambridge student. Thank you very much. Please subscribe my channel, hit the bell icon, and share it with your friends. Thank you very much. Have a nice day.